Hello there and welcome to Science After Hours. Tonight, we are going to wash away the day. We are going to explore the slippery, scented, bubbling world of a substance that changed human history. It is a simple object, often sitting quietly by the sink or resting in a porcelain dish, yet it holds the power to destroy viruses, dissolve grease, and separate the clean from the unclean. We are talking, of course, about soap. It is a product of chemistry and cooking, a marriage of fat and ash that creates something entirely new. From the ancient cauldrons of Babylon to the modern triple-milled bars of France, soap has been our constant companion in the pursuit of purity. If you enjoy these gentle journeys into the chemistry of everyday life, you can like and subscribe, or simply share a thought down in the comments. It helps others find their way here too. One sleepy soul let it, but for now, settle in. Imagine the warmth of a bath, the smell of lavender and steam, and the soft pop of a bubble. Allow yourself to drift as we explore the chemistry of clean. Let's begin. Soap is a salt. We usually think of salt as the white crystals we sprinkle on our food, but in the language of chemistry, a salt is simply the result of an acid reacting with a base. Soap is chemically defined as a salt of a fatty acid. When you take a fat like olive oil or tallow and mix it with a strong alkali, they neutralize each other. The result is a crystalline structure that looks nothing like the oil and nothing like the alkali. It becomes a salt. Imagine the transformation. A greasy liquid and a dangerous chemical combining to form a solid, safe, cleaning bar. It is one of the oldest and most useful chemical reactions known to mankind. Soap is not just a cleaner. It is a molecular truce between opposites. Babylon held the first recipe. The history of soap is ancient. The earliest recorded evidence of soap-making materials was found in excavations of ancient Babylon dating back to around 2800 BC. Clay cylinders were discovered containing a soap-like substance, along with inscriptions describing the recipe. The Babylonians boiled fats with ashes. Imagine a clay pot sitting over a fire nearly 5,000 years ago. A person stirs the mixture, watching it thicken. They likely used it for washing wool and cotton in preparation for weaving, rather than for personal hygiene. It reminds us that the quest to clean our world is as old as civilization itself. Before we built great empires, we learned how to make bubbles. Mount Sapo is the legend of the name. Where does the word soap come from? There is a persistent Roman legend about Mount Sapo. According to the story, this was a site where animal sacrifices took place. The fat from the animals would melt and mix with the wood ashes from the sacrificial fires. When it rained, this mixture of fat and ash, essentially raw soap, would wash down the mountain into the clay soil of the Tiber River. Women washing clothes in the river noticed that the clay from this specific spot made their cleaning much easier and produced a rich lather. While historians debate the accuracy of this tale, it is a beautiful image. Soap as an accidental gift from the gods, flowing down the mountain to help the people below. Soap has two hands. The magic of soap lies in its molecular shape. A soap molecule is amphiphilic, which means it has a split personality. It looks like a tadpole. The head of the molecule is hydrophilic. It loves water. The tail of the molecule is hydrophobic. It hates water, but it loves oil and grease. Imagine this molecule floating in your sink. The tail dives into the grease on your plate, anchoring itself there to escape the water. The head stays sticking out into the water. This unique structure allows soap to act as a bridge. It grabs the dirt with one hand and the water with the other, allowing two things that normally hate each other, oil and water, to hold hands and wash away. The micelle is a trap. When you wash your hands, the soap molecules don't just float randomly. They organize. They form microscopic spheres called micelles. Imagine a ball where all the oil-loving tails are pointing inward, trapping a droplet of grease in the center, while all the water-loving heads form the outer shell. The dirt is essentially locked inside a cage made of soap. This cage makes the grease soluble in water. When you rinse your hands, the water grabs the outside of the micelle and pulls the whole thing, dirt and all, down the drain. It is a microscopic kidnapping operation happening every time you wash up. Saponification is the transformation. The chemical reaction that creates soap has a beautiful name, saponification. It comes from the Latin sapo, meaning soap. It is an exothermic reaction, meaning it creates its own heat. If you mix oils and lye in a pot, the mixture will heat up on its own as the molecules rearrange themselves. It thickens from a liquid into a pudding-like state called trace. Imagine the alchemy of it. You are not just mixing ingredients, you are witnessing a permanent chemical change. Once saponification is complete, you can never get the oil or the lye back. They have become one. It is a process of total and irreversible becoming. The Egyptians bathed in oil and salt, while the Babylonians used soap for textiles. The ancient Egyptians were pioneers of personal hygiene. The Ebers Papyrus, a medical document from 1500 BC, describes combining animal and vegetable oils with alkaline salts to create a soap-like substance for washing the body. They also used it to treat skin diseases. Imagine the bathhouses of the Nile, scented with essential oils. The Egyptians valued cleanliness as a spiritual duty. They bathed several times a day. Their soap was softer and more paste-like than our modern bars, but the chemistry was the same. They were scrubbing away the desert sand with the chemistry of the river valley. True soap needs fat and lye. There is no soap without lye. This is a fact that surprises many people. Lye sodium hydroxide is a caustic base that can burn skin. Yet, it is the essential catalyst. You can make soap from olive oil, coconut oil, beef tallow, or shea butter, the acid. But you must react it with lye, the base. Some people fear lye in their ingredients list, but in a properly made bar of soap, no lye remains. It is all used up in the reaction. Imagine the lye as a fire that burns the wood. Once the fire is out, only the ash, the soap, remains. The danger transforms into safety. Glycerin is the hidden moisturizer. When you make soap, you actually create two things: soap and glycerin. Glycerin is a humectant, meaning it attracts moisture from the air to your skin. It is a natural byproduct of saponification. However, in many commercial soaps, the manufacturers remove the glycerin to sell it separately for expensive lotions and creams. This is why some cheap grocery store soaps dry out your skin. They have had their soul removed. Handmade soap retains its glycerin. Imagine a soap that feeds your skin while it cleans it. Glycerin is the gentle, moisturizing ghost that haunts the soap bar. Most soap is actually detergent. If you look at the package of your body wash or beauty bar, you might not see the word soap. You might see beauty bar, cleansing bar, or body wash. This is because they are technically synthetic detergents, or synthets. True soap has a high pH, around 9 or 10. Detergents are petroleum-based products designed to have a neutral pH closer to human skin. They were developed to work better in cold water and not leave scum. Imagine a laboratory creating a cleaner that mimics nature but performs with machine-like efficiency. While effective, they lack the romance and history of true soap. Hard water creates the ring. We have all seen the stubborn ring around the tub. This is not dirt, it is chemistry. It happens when true soap meets hard water, water rich in calcium and magnesium minerals. The soap molecules react with the calcium instead of the water. They turn into an insoluble substance called lime soap, or soap scum. It creates a gray sticky film that clings to the tiles. Imagine the soap trying to do its job but getting distracted by the minerals. It precipitates out of the water, falling like gray snow. It is the one weakness of traditional soap. It struggles to fight the geology of the water itself. Castile soap is pure olive. One of the most famous names in soap is Castile. Historically, this referred to soap made in the Castile region of Spain using 100% olive oil. Before this, many European soaps were made with animal fats that smelled strong. Olive oil soap was white, hard, and odorless. It was a luxury item for royalty. Imagine a bar of soap that feels like smooth white marble and lathers with a rich, creamy slime rather than fluffy bubbles. True Castile soap is renowned for its gentleness. It is the grande dame of the soap world, elegant and simple. Ivory soap floats by mistake. The brand Ivory is famous for the slogan, "It floats." But this iconic feature was reportedly an accident. In 1879, a worker at the Procter & Gamble factory forgot to turn off the mixing machine during his lunch break. The machine whipped a massive amount of air into the batch. Instead of throwing it out, they molded it into bars and shipped it. Customers loved the floating soap. It didn't get lost in the murky bathwater. Imagine a mistake becoming a marketing empire. The soap is essentially a frozen foam, a bar filled with millions of microscopic air bubbles that act like life jackets. Soap was taxed as a luxury. In 17th century England, soap was so prized that it was heavily taxed. The soap tax was a major source of revenue for the crown. Soap makers were required to sleep at the factory to prevent them from producing illegal, untaxed soap at night. The tax was so high that soap became a luxury for the rich, while the poor suffered from hygiene-related diseases. Imagine a world where cleanliness was contraband. The tax wasn't repealed until 1853, costing the Treasury over £1 million, but finally allowing the public to wash freely. It was a victory for public health over profit. Soap operas sold cleanliness. The term soap opera is a direct nod to the history of advertising. In the 1930s, radio dramas were incredibly popular with housewives. Soap manufacturers like Procter & Gamble realized this was the perfect audience. They sponsored the shows, advertising products like Oxydol and Dews. The dramas were melodramatic and emotional, designed to keep the listener hooked so they would hear the commercial for soap flakes. Imagine the emotional roller coaster of a radio romance interspersed with promises of whiter laundry. The The entertainment industry and the cleaning industry grew up together, intertwined by the need to sell bubbles. Liquid soap arrived late. For thousands of years, soap was a solid bar. Liquid soap is a relatively modern invention for the home. While liquid versions existed for industrial use, it wasn't mass-marketed for hand washing until the late 1970s. With the Minnetonka Corporation's soft soap, they famously cornered the market by buying up the world's entire supply of plastic pump dispensers, preventing competitors from launching their own versions for a year. Imagine a world without the pump bottle on the sink. It changed the way we wash, making it faster and arguably more sanitary, turning the ritual of lathering a bar into a quick pump and go. Bar soap is not dirty. A common myth is that bar soap is unhygienic because it is touched by dirty hands. People fear that bacteria live on the surface of the bar. However, studies have shown that while bacteria might sit on the wet slime of the soap, they are not transferred to the next user. They are washed away as soon as you create lather. The soap is a hostile environment for germs. It destroys their cell membranes. Imagine the bar of soap as a self-cleaning surface. It might look messy, but it is chemically incapable of hurting you. You can share a bar with a stranger and be perfectly safe. Lye is the invisible worker. We mentioned lye earlier, but its nature deserves a closer look. Sodium hydroxide is a white, crystalline powder that absorbs water from the air so fast it dissolves itself. It is incredibly caustic. If you touch raw lye, it turns the oils in your skin into soap right on your body, which causes a chemical burn. Soap makers wear goggles and gloves, treating the lye with extreme respect. Imagine a dangerous white powder that is the ancestor of the gentle, soothing bar you use on a baby. The transformation is absolute. The danger is consumed by the fat, leaving only the clean. Nabolsi soap is built into towers. In the West Bank city of Nablus, soap making is an art form that has remained unchanged for centuries. Nabolsi soap is made from olive oil, water, and alkaline sodium compound. After the soap is cooked, it is poured onto the floor to cool. Then, workers cut it into cubes and stack them in mesmerizing geometric towers that reach the ceiling. These towers allow air to circulate around each bar. Imagine walking into a cool stone hall filled with towers of soap, smelling of earth and olives. The soap ages there for months or even years, turning from green to a pale, hard sandstone color. It is architecture made of cleaning. Aleppo soap is the ancient ancestor. Before there was Castile soap or Marseille soap, there was Aleppo soap from Syria. It is considered the oldest hard soap in the world. Its secret ingredient is laurel berry oil. The soap is cooked for days and then aged for up to 9 months. As it ages, the outside turns a golden brown, while the inside remains a vibrant emerald green. Imagine cutting into a bar of antique soap to find a green jewel inside. The laurel oil gives it a spicy, medicinal scent and antibacterial properties. It is a soap that carries the history of the Silk Road in its scent. Bubbles love spheres. Why is a soap bubble always round? You can blow it through a square wand, a triangular wand, or a star-shaped wand, but the moment the film leaves the frame, it snaps into a perfect sphere. This is the law of minimal surface area. A sphere is the shape that encloses the maximum volume with the minimum amount of surface skin. The soap film is under tension, pulling itself as tight as possible. Imagine the bubble trying to conserve its energy. wrapping itself into the most efficient package in the universe. It is nature's perfect geometry, a fleeting planet made of air and shine. Iridescence is interference. The swirling colors on a soap bubble, the pinks, teals, and golds, are not caused by pigments. They are caused by light waves interfering with each other. A soap film has an outer layer of soap, an inner layer of water, and another layer of soap. Light hits the outer layer and reflects, but some light goes through and reflects off the inner layer. These two reflections crash into each other. If the crests of the waves align, the color is bright. If they cancel out, the color disappears. Imagine the bubble as a prism that changes color depending on how thick the water is. As the water evaporates and gravity pulls it down, the colors shift and swirl. You are watching the thickness of the wall change in real time, measured in nanometers of light. You can freeze a bubble. If you blow a soap bubble outdoors on a day when the temperature is well below freezing, around 10 degrees Fahrenheit or minus 12 degrees Celsius, something magical happens. The bubble doesn't pop, it freezes. Crystals of ice begin to form on the surface, usually starting at the bottom and growing upward, like ferns on a window pane. Imagine a glass ornament forming in midair. The bubble becomes a solid, fragile shell. However, once it thaws, it usually shatters instantly because the ice crystals disrupt the surface tension that holds the film together. It is a moment of impossible fragility, a frozen breath that lasts only as long as the cold holds it. Soap drowns insects. Gardeners often spray soapy water on plants to get rid of aphids and other pests. This isn't because the soap poisons them, it drowns them. Insects breathe through tiny holes in their bodies called spiracles. Water usually beads up and rolls off insects because of surface tension, but soap breaks that tension. The water spreads out and floods the spiracles, suffocating the bug. Imagine the soap removing the invisible shield that protects the insect from the wetness of the world. It is a mechanical defeat, a simple change in the physics of the water that turns it deadly to the very small. Milled soap is dense. Have you ever used a bar of French milled or triple milled soap? It feels heavy, smooth, and lasts forever. This is because of the manufacturing process. After the soap is made, it is shredded into flakes and run through heavy steel rollers. Once, twice, or 3 times. This squeezes out all the air bubbles and excess water, pressing the soap crystals into a tight, uniform lattice. Imagine compressing a fluffy cake into a dense energy bar. The result is a soap that doesn't turn into mush in the dish. It is a bar refined by pressure, made to endure. Transparent soap uses alcohol. How do you make a bar of soap you can see through? The answer is solvents. Pear soap. The famous amber-colored transparent bar is made by dissolving the soap compound in alcohol and sugar syrup. This aligns the soap crystals so perfectly that light can pass straight through them. Imagine looking through a window made of cleaning power. It requires a precise balance. If you cook it too long, it clouds up. Transparent soap is a visual trick, suggesting purity and lightness, proving that chemistry can be clear as glass. Grease-built explosives. During World War II, housewives in America and Britain were instructed to save their bacon, grease, and meat drippings. They took cans of fat to the butcher. But this wasn't just for soap, it was for bombs. The glycerin removed during the soap-making process is the key ingredient in nitroglycerin. Explosives. 1 pound of fat contained enough glycerin to make about a pound of explosives. Imagine the kitchen connected to the front lines. The waste of the breakfast table was transformed into the firepower of the war. It is a stark reminder of the industrial utility of fats. They can clean a uniform or destroy a bridge. The first liquid soap patent. While soft soap conquered the home in the 70s, the first patent for liquid soap was granted way back in 1865 to a man named William Shepard. He discovered that by dissolving small amounts of soap in water and adding ammonia, he could create a thick liquid. It was originally marketed for public places to avoid the mess of bar soap. Imagine the Victorian era flirting with the convenience of the pump. It took over 100 years for the idea to truly catch on, proving that sometimes an invention is ahead of the cultural habit required to use it. Black soap is ash and oil. True African black soap, os dudu, originates from West Africa, particularly Ghana and Nigeria. It gets its deep brown or black color not from dyes, but from the ash of locally harvested plants like cocoa pods, plantain skins, or palm tree leaves. The ash provides the alkali, potash, needed to turn the shea butter and palm oil into soap. Imagine a soap cooked in a cauldron over an open fire. Smelling of earth and smoke, it is crumbly and soft. It is one of the few soaps that is still made almost entirely by hand in village cooperatives, connecting the modern user directly to the earth of the savannah. Superfatting is a luxury. When making soap, you can calculate the exact amount of line needed to turn every molecule of oil into soap, or you can add extra oil. This is called superfatting. By leaving 5% or 10% of the oil unsaponified, you create a bar that cleans but also deposits a thin layer of oil back onto the skin. Imagine a wash that moisturizes. It is a balancing act. Too much free oil and the soap will spoil or feel greasy. Too little and it strips the skin. It is the art of leaving a little bit of the raw ingredient behind to soften the blow of the chemistry. Soap film is microns thick. The wall of a soap bubble is incredibly thin. It ranges from 10 nanometers to about 1,000 nanometers. To put that in perspective, a human hair is about 100,000 nanometers thick. If a soap bubble were the size of the Earth, its wall would be less than an inch thick. Imagine a structure so tenuous it is barely there, yet strong enough to hold a sphere of air against the pressure of the atmosphere. It is the thinnest thing you can see with the naked eye, a shimmering curtain of molecules dancing on the edge of existence. Detergents fight hard water. We mentioned the ring around the tub. During World War I and II, there was a shortage of animal and vegetable fats for soap. Scientists had to invent a cleaner that didn't need fat and didn't react with hard water minerals. They turned to petroleum byproducts and created synthetic detergents. These molecules don't grab onto calcium. They ignore it. Imagine a cleaner that works in seawater or well water without complaining. Detergents allowed us to wash clothes in any condition. They are the workhorses of the laundry room, chemically engineered to bypass the limitations of geology. Potassium makes it liquid. If you use sodium hydroxide, you get a hard bar of soap. But if you use potassium hydroxide, potash, you get a soft, gooey paste that can be diluted into liquid soap. Potassium ions are larger than sodium ions. They prevent the soap molecules from packing together into a tight crystal lattice. Imagine the molecules trying to hold hands, but the potassium gets in the way, keeping the mixture fluid. It is a simple switch on the periodic table, moving down one row from sodium to potassium, that changes the entire state of matter from solid to liquid. The soap plant stuns fish. Nature invented soap long before we did. The soap plant, Chlorodyllum pomeridianum, native to California, has a bulb full of saponins. Native Americans used it for washing, but also for fishing. By crushing the bulbs and throwing them into a stream, the saponins would foam up and remove oxygen from the water, temporarily stunning the fish so they floated to the surface. Imagine fishing with bubbles. It is a gentle, chemical way to harvest food, using the plant's natural defense mechanism as a tool. Soap carving is ephemeral art. In Thailand, there is a tradition called Kaya Sa Luk, the art of carving fruit and vegetables. This evolved into carving soap. Artists take a simple bar of commercial soap and use tiny knives to sculpt intricate flowers, dragons, and landscapes. Imagine a lotus flower blooming from a bar of dove or ivory. The soap is soft, allowing for incredible detail, but it is fragile. The scent of the soap becomes part of the art. It is a sculpture that is destined to dissolve or dust away. A temporary beauty carved from a household utility. Romans scraped instead of scrubbed. Before soap was common in Rome, bathing was a mechanical process. Men would cover themselves in olive oil to loosen dirt and sweat. Then they would use a curved metal tool called a strigil to scrape the oil dirt mixture off their skin. Imagine the sensation of metal scraping oil from your arm. It exfoliates and cleans, but without the bubbles we are used to. The oil acted as the solvent. It reminds us that clean hasn't always meant soapy. For centuries, it meant being oiled and scraped like a piece of machinery. Bacon grease makes soap. You can make soap from almost any fat. In the American frontier, nothing was wasted. When a pig was butchered, the fat was rendered into lard. When cattle were killed, the fat became tallow. Even the grease from cooking bacon was saved. Soap made from bacon grease actually doesn't smell like bacon once the chemical reaction is done. It just smells like soap. Imagine the frugality of the pioneer life. The waste from breakfast became the tool to wash the dishes for dinner. It is a perfect cycle of domestic chemistry. The FDA definition is strict. In the United States, the legal definition of soap is narrow. To be labeled as soap, it must be made mainly of fats and alkali, and its only claim can be, it cleans. If a product claims to moisturize, deodorize, or whiten, the FDA classifies it as a cosmetic or a drug. This subjects it to different regulations. Imagine a bar of soap having an identity crisis. Most of what we buy is legally a cosmetic. True soap is a humble product with a humble legal standing. It is allowed to exist simply to clean, nothing more. Antibacterial soap is unnecessary. For years, store shelves were full of antibacterial soaps containing triclosan. But in 2016, the FDA banned many of these ingredients. Why? Because science showed they work no better than plain soap and water. Plain soap lifts the germs off the skin so they can be rinsed away. It doesn't need to poison the bacteria, it just needs to evict them. Imagine the soap as a bouncer throwing unruly guests out of the club. You don't need to kill the guests. You just need to get them out the door. plain soap is the ultimate bouncer. Soap nuts grow on trees. In the Himalayas, there grows a tree called Sapindus mucurosi. Its fruit, the soap nut, contains high levels of natural saponin. If you put a handful of these dried berries in a cotton bag and toss them in your washing machine, they foam up and clean your clothes. Imagine doing laundry with berries. They are reusable and compostable. It is a cleaning method that requires no factories, no lye, and no plastic bottles. It is simply a fruit that knows how to wash. It reminds us that nature often provides the solution before we even invent the problem. Marseille soap has a golden rule. In France, soap is serious business. By a 1688 edict from King Louis XIV, Savon de Marseille must contain at least 72% vegetable oil to bear the authentic stamp. Originally, it had to be olive oil. The king banned the use of animal fats to protect the quality of the soap. Imagine a soap police force checking the vats. The traditional blocks of Marseille soap are massive cubes, often stamped on all 6 sides. They are green or beige, smelling of the crushed olives. It is a product defined by a 300-year-old law, ensuring that what you hold in your hand is the same pure block that a French washerwoman held in the 17th century. Soapstone is a rock imposter. Soapstone, or steatite, is not soap. It is a metamorphic rock rich in talc. But if you rub your thumb across it, it feels greasy and slippery, exactly like a dry bar of soap. This soapy texture comes from the softness of the talc mineral. It is so soft, you can carve it with a fingernail. Ancient people carved bowls and statues from it. Imagine a rock that feels like it wants to lather. It is a geological coincidence. A stone mimicking the texture of fat. Urine was the original ammonia. Before we had bottles of cleaning fluid, we had chamber pots. Urine contains urea, which breaks down into ammonia over time. Ammonia is a fantastic cleaner. It cuts grease and whitens fabric. Romans would place buckets on street corners for citizens to fill. This urine was collected and taken to the Folonica, laundry, where workers would stomp on clothes, soaking in vats of stale urine. Imagine the smell of the ancient laundromat. It was dirty work, but it resulted in brilliant white togas. It is a reminder that the chemistry of cleaning has humble and sometimes smelly origins. The most expensive soap holds diamonds. While a bar of ivory costs $1, the Qatar Royal soap costs roughly $2,800. It is infused with gold dust, olive oil, and virgin honey, and encrusted with diamonds. Imagine washing your hands with a bar worth more than a car. The gold and diamonds do nothing for the cleaning power. They are pure spectacle. It transforms the humble act of washing into a performance of extreme wealth. It proves that even the most basic necessity can be gilded if the desire is there. Florence Nightingale prescribed soap. In the mid-19th century, hospitals were dirty places. Surgeons wiped their knives on their coats. Infection was rampant. Florence Nightingale, the mother of modern nursing, championed the radical idea of cleanliness. She didn't know about germs yet, but she knew that dirt brought death. She demanded soap, hot water, and fresh air for the soldiers in the Crimean War. Imagine the smell of carbolic soap replacing the smell of decay. Her insistence on scrubbing floors and washing hands saved thousands of lives. Soap became a medical device, a weapon against the invisible enemy of infection. Saponin is the plant's soap. Quinoa, the popular grain, has a bitter coating called saponin. If you rinse quinoa in a bowl of water, you will see foam appear. This is natural soap. The plant produces it to taste bad to insects and birds. Imagine a grain defending itself with bubbles. Indigenous peoples use this runoff to wash clothes. It is a reminder that the boundary between food and cleaner is blurry. The same chemistry that protects the seed can wash the shirt. Skin is acidic. Soap is alkaline. There is a chemical war happening on your face. Human skin has an acid mantle, a protective barrier with a pH of around 5.5. True soap is alkaline with a pH of 9 or 10. When you wash with true soap, you temporarily strip away the acid mantle and raise the pH of your skin. This is why skin can feel squeaky clean. The oils are gone. Healthy skin restores its pH balance within an hour or so. Imagine the skin breathing a sigh of relief as it rebuilds its acid wall. This is why modern pH-balanced cleansers became popular. They try to clean without upsetting the chemical balance of the body. Shaving soap softens the keratin. A dry beard hair is as tough as copper wire of the same thickness. Cutting it is hard work for a razor. Shaving soap does more than just lubricate the skin. It hydrates the hair. The alkaline lather swells the hair shaft and softens the keratin protein. Imagine the hair relaxing, losing its stiffness. A wet, soapy beard hair is exponentially easier to cut than a dry one. The brush acts as a whisk, whipping air into the soap to create a thick cushion. It turns the violent act of scraping a blade across the face into a smooth, ritualistic glide. Bubbles pop when the water leaves. A soap bubble is a sandwich. Soap, water, soap. The bubble pops when the water in the middle evaporates. As the water layer gets thinner, the bubble gets weaker. Gravity also pulls the water to the bottom of the bubble. If you watch closely, you can see the top of the bubble turning silvery and then transparent just before it bursts. This is the black film stage. Imagine the wall becoming so thin it can no longer interact with light. The pop is the moment the water gives up. To make a bubble last longer, you must slow the evaporation, which is why bubbles last longer on humid, rainy days. Glycerin makes it clear. Titanium makes it white. If you look at a bar of soap, its look is determined by additives. A clear soap has glycerin and sugar. A solid white soap usually contains titanium dioxide. This is a white pigment found in paint and sunscreen. Imagine adding white paint to the soap to make it look creamy and substantial. Without it, many soaps would look yellowish or translucent, like frozen fat. We associate whiteness with purity, so we engineer the soap to look the part. Lava soap uses a volcano. For mechanics and painters, regular soap isn't enough to remove grease and tar. They need grit. Lava soap contains ground-up pumice, volcanic rock. Imagine washing your hands with a stone. The pumice acts as tiny chisels, scraping the dirt off the skin while the soap lifts it away. It is exfoliation on an industrial scale. It connects the bathroom sink to the volcano, using the lightest rock on Earth to do the heavy lifting of hygiene. Cold process takes patience. There are two main ways to make handmade soap. Cold process involves mixing the fats and lye at warm temperatures, pouring it into a mold, and then waiting. The soap is safe to use after a few days, but it is full of water. It needs to cure for 4 to 6 weeks. Imagine rows of soap bars sitting on a drying rack in a dark room, slowly hardening. Like cheese or wine, soap gets better with age, the water evaporates, the bar shrinks slightly, and the lather becomes milder. It is a slow craft for a fast world. Hot process cooks the soap. If you are impatient, you use hot process. You cook the soap mixture in a slow cooker or a double boiler. You force the gel phase to happen with external heat. The result is a rustic, bumpy bar that can be used the next day. Imagine a thick, mashed potato texture being spooned into a mold. It lacks the smooth finish of cold process, but it has the charm of a home-cooked meal. It is soap made with fire, ready to work immediately. Salt bars are hard as rocks. If you add a large amount of sea salt, 100% of the oil weight, to a soap recipe, you create a salt bar or spa bar. The salt doesn't dissolve in the soap batter. Instead, the soap hardens around the salt crystals. The result is a bar incredibly hard, white and heavy. It polishes in the shower like a river stone. Imagine washing with a piece of white granite that lathers, the salt exfoliates and draws toxins, while the soap cleans. It creates a creamy, low lotion-like lather that feels vastly different from regular soap. Bubbles turn black before dying. We return to the bubble. Just before a soap bubble pops, the top of it loses its color. The interference of light waves stops because the film is thinner than the wavelength of visible light. It appears as a dark, swirling spot that grows rapidly. Physics calls this a black film. Imagine the bubble turning invisible before it turns into nothing. It is a warning sign. When you see the black hole open in the rainbow, the end is milliseconds away. Washing mouths out was real. The idiom, "wash your mouth out with soap," was a literal punishment for swearing in the 19th and 20th centuries. The alkaline taste of soap is bitter and triggers a gag reflex. Imagine the sharp, chemical taste of discipline. It physically cleansed the dirty words from the tongue. While we view it as abusive today, it serves as a cultural marker of how deeply we linked moral purity with physical cleanliness. Dirty language required a detergent. Soap cleaned wool first. For the first few thousand years of its existence, soap wasn't for humans. It was for industry. The Romans and Celts used soap primarily to wash the lanolin, grease, out of raw wool before it could be dyed. Imagine a vat of smelly, gray soap liquor washing fleece. If you didn't wash the wool, the dye wouldn't stick. The textile industry drove the soap technology. We were secondary. We only started washing our bodies regularly when soap became cheap enough to waste on skin. Zero-gravity bubbles are perfect. On Earth, large soap bubbles wobble and distort into jelly bean shapes because of air currents and gravity dragging the liquid down. But on the International Space Station, a soap bubble is a perfect, unwavering sphere. It can last for a long time. Astronauts can inject water or air into the bubble, creating bubbles inside bubbles. Imagine a floating solar system of soap. Without gravity to drain the water to the bottom, the film stays uniformly thick. It is the Platonic ideal of a bubble, existing only in the vacuum of orbit. Sugar makes bubbles strong. If you want to blow giant bubbles that don't pop, add sugar or corn syrup to your soap mix. The sugar dissolves in the water layer of the bubble film. It slows down evaporation. It creates a sticky, elastic bond that allows the bubble to stretch huge distances without snapping. Imagine a bubble the size of a car wobbling in the wind. The sugar acts as the structural steel in the skyscraper of the bubble. It turns a fragile toy into a resilient wonder. Saddle soap feeds leather. Leather is skin. Like human skin, it needs to be cleaned and moisturized, or it cracks. Saddle soap is a specific formulation containing beeswax and lanolin. It doesn't just clean the mud off a saddle, it replaces the natural oils that the leather lost. Imagine rubbing a yellow paste into worn leather, watching the color deepen and the cracks fade. It is a conditioner. It reminds us that cleaning isn't just about removing dirt, it's about maintenance. It is keeping the material alive. Soap making day was an event. For early American settlers, making soap wasn't a hobby. It was an annual chore of survival. They saved fat from cooking all year long. They saved wood ashes from the fireplace all winter long. Then, on soap making day, usually in the spring, the cauldrons came out. Imagine a massive iron pot bubbling over an outdoor fire. The smell would have been pungent. It was dangerous, hot work, handling boiling fat and caustic lye water. But the result? A year's supply of soft, jelly-like soap meant cleanliness for the family. It was a day that turned the waste of the year into the hygiene of the next. Water through ashes makes lye. How did settlers get lye without a chemical factory? They used a leaching barrel. They filled a barrel with hardwood ashes and poured rainwater over it. The water trickled down through the ash, picking up potassium carbonate, potash. Brown, caustic liquid dripped out of the bottom. To test if it was strong enough, they would float an egg or a potato in it. If it floated, it was ready to dissolve fat. Imagine extracting chemistry from a fireplace. It connects the tree to the soap. The wood burned to warm the house, and the ashes remain to clean the clothes. Soap absorbs odors. A bar of soap is porous. If you place a wrapped bar of lavender soap in a suitcase or a drawer, it acts like a solid air freshener. But more than that, it can absorb musty smells. Travelers have long used this trick to keep clothes smelling fresh on long journeys. Imagine opening a suitcase after a flight and being greeted not by the smell of travel, but by the clean scent of a rose garden. The soap is active even when dry, trading its scent molecules for the stale air of the luggage. Soap cures leg cramps. This is one of the strangest folk remedies in existence. Many people swear that placing a bar of soap under the bed sheets near the legs prevents nocturnal leg cramps. Science is skeptical. Is it the placebo effect? Or does the soap release volatile compounds like limonene that relax the muscles? We don't know for sure. Imagine sleeping with a bar of ivory at your feet. It sounds uncomfortable, yet for thousands, it is the only thing that works. It is a mystery where the chemistry of soap meets the psychology of pain. Soap dissolves viruses. In 2020, we all relearned the power of hand washing. Why does soap kill a virus like the coronavirus? It is because the virus is essentially a ball of genetic material wrapped in a lipid, fat envelope. Remember, soap loves fat. When you wash your hands, the soap molecules pry their way into the virus's fatty shell. They tear it apart. Imagine the soap popping the virus like a balloon. The genetic material spills out and is destroyed. Hand sanitizer works, but soap is a demolition crew. It physically dismantles the enemy structure. Castile is a region in Spain. We mentioned Castile soap earlier, but the geography is important. The Kingdom of Castile in Spain had endless olive groves. They supplied the royal courts of Europe with this white, hard soap. Before Castile soap, Northern Europe used soft, smelly soap made from animal fat and wood ash. The Spanish soap, made with soda ash from burning sea plants and olive oil, was a revolution. Imagine the trade routes carrying white bars north. It was a status symbol. To smell like olive oil was to smell like nobility. Soap makers formed guilds. In 7th century Europe, soap making became a profession. By the Middle Ages, soap makers in Italy and France had formed powerful guilds. They kept their recipes secret. In some places, craftsmen were forbidden from staying in the same cauldron room with master soap makers to prevent theft of trade secrets. Imagine a secret society dedicated to bubbles. They protected the ratio of oil to ash as fiercely as goldsmiths protected their metal. Cleanliness was becoming an industry. Floating soap is less dense. Why does ivory soap float? It is simple physics. Density is mass per unit volume. Water has a density of 1.0 grams per cubic centimeter. If an object is less dense than 1.0, it floats. The air whipped into the floating soap lowers its density to about 0.9. It is lighter than water. Imagine a bar of soap acting like a boat. Most other soaps are dense blocks of fat and salt sinking like stones to the bottom of the tub. The air makes the difference. It is an invisible ingredient that changes the behavior of the bar completely. Soda ash is the white dust. If you buy handmade soap, you might see a white powdery film on the surface. Soap makers call this soda ash or soap bloom. It happens when the lye in the raw soap reacts with carbon dioxide in the air while it is curing. It creates a thin layer of sodium carbonate. It is harmless and washes off the first time you use it. Imagine the air trying to turn the soap back into salt. It is a visual flaw, but a sign that the soap is truly handmade and reactive to its environment. Pine tar smells like a campfire. Pine tar soap is black, sticky, and smells intensely of campfire smoke and turpentine. It contains actual pine tar, a sticky substance produced by burning pine roots. It has been used for centuries to treat eczema, psoriasis, and dandruff. Imagine washing with the essence of a burnt forest. It doesn't smell clean in the floral sense. It smells medicinal and ancient. It soothes the skin by reducing inflammation. It is the forest floor distilled into a bar. Milk makes it creamy. You can make soap with water, but you can also make it with milk, goat milk, coconut milk, or buttermilk. The natural sugars in the milk, lactose, boost the lather, making it bubbly. The fats in the milk add creaminess, but making it is tricky. The lye gets so hot it can scorch the milk, turning the soap orange and smelling of ammonia. Soap makers must freeze the milk first to keep it cool. Imagine washing with a solid bar of cream. It feels luxurious, a step closer to lotion than detergent. Laundry bluing is an optical trick. White fabrics turn yellow over time. To fix this, old-fashioned laundry soaps often included a bit of blue dye, or bluing. Blue is the opposite of yellow on the color wheel. A tiny bit of blue tint cancels out the yellow, making the fabric appear bright white to the human eye. Imagine adding blue to make white. It is a trick of the light. a visual correction built into the soap. We aren't really removing the yellow. We are hiding it with blue. Stainless steel removes onions. You can buy a soap shaped like a bar of steel. It doesn't lather. You rub it on your hands underwater to remove the smell of garlic or onions. Sulfur molecules from the onion bind to your skin, creating the smell. The chromium in the stainless steel binds to the sulfur, pulling it off your skin and onto the metal. Imagine a magnet for smell. It transfers the odor from biological, hand, to mineral, steel. It effectively washes the smell away without any bubbles at all. The hydrophobic effect drives the clean. Why does soap work? It is driven by the hydrophobic effect. The water molecules want to stick to each other. Hydrogen bonding. The oil wants to stay away. The soap gives the oil a way to hide. The oil dives into the center of the mice shell not because it loves the soap, but because the water is pushing it away. Imagine the water squeezing the oil out of the way and the soap catching it. It is a dance of exclusion. Cleaning is essentially the water rejecting the dirt and the soap providing a lifeboat for the rejected particles. Bubbles can be square. We said bubbles are spheres, but you can force them to be square. If you dip a wire frame shaped like a cube into soap solution, the film will stretch across the edges, meeting in the center. If you then blow a bubble into the center of that structure, it will fill the space and become a cube. Imagine a box made of liquid. The tension pulls the walls flat. It proves that while nature prefers spheres, it will obey geometry if forced. It is a structural marvel, a moment where fluid acts like a solid beam. Dr. Bronner's is a sermon. If you have ever read a bottle of Dr. Bronner's magic soap, you know it is covered in thousands of tiny words. Emanuel Bronner was a third-generation soap maker who used his labels to preach his all-one God faith. He believed his soap could unite humanity. Imagine a soap bottle that serves as a manifesto. The peppermint soap tingles the skin, while the label tingles the mind with moral philosophy. It is one of the strangest and most successful marketing strategies in history, proving that soap can carry a message along with the lather. Curved bars dry faster. Why is a bar of soap usually curved? Not a perfect brick. The curve fits the hand, yes. But it also minimizes the contact area with the soap dish. If a flat bar sits in a puddle, it turns to mush, soap slime. A curved bar rests on points, allowing air to flow underneath and dry it out. Imagine the architecture of the bar designed to save itself. The shape extends the life of the product. It is engineering for the bathroom sink. Soap creates mechanical removal. We think soap kills germs chemically, but mostly it just makes them slippery. The friction of rubbing your hands together lifts the germs off the skin. The soap surrounds them so they can't stick back on. Then, the water washes them away. Imagine the germs sliding off your hands like skaters on ice. You aren't destroying them. You are evicting them. This is why scrubbing for 20 seconds is key. The soap needs time to make everything slippery enough to let go. Salt thickens the mix. If you are making liquid soap and it is too runny, you add salt water. The salt ions interfere with the micelles, causing them to elongate and tangle together. This tangling thickens the liquid into a gel. Imagine microscopic threads getting knotted. It changes the texture from water to honey. But if you add too much salt, the soap structure collapses and it turns back into water. It is a delicate chemistry curve. A pinch of salt creates luxury. A spoonful destroys it. Tallow makes it hard. Beef fat, or tallow, has been the primary ingredient in soap for centuries. It is high in stearic acid. This creates a very hard white bar with a creamy, stable lather. Vegetable oils tend to make softer soap. Imagine the difference between butter, soft, and wax, hard. Tallow soap lasts a long time in the shower. While plant-based soaps are popular now, tallow was the gold standard for generations because it made a bar that didn't melt away in a week. It utilized the whole animal, wasting nothing. Lard makes a conditioning bar, while tallow makes a hard bar. Lard, pig fat, makes a soap that is famously conditioning. Its fatty acid profile is surprisingly similar to human skin oil. In the old days, lard soap was the premium laundry soap because it cleaned gently without roughing up the fabric. Imagine a soap so mild it feels like lotion. Despite its humble origin, it creates a bright white bar with a creamy lather. It reminds us that sometimes the simplest ingredients are the most compatible with our biology. Coconut oil is a bubble machine. If you want big fluffy bubbles, you use coconut oil. It is rich in lauric acid, which is highly soluble and lathers explosively, even in salt water. This is why sailor's soap is often pure coconut oil. It works in the ocean. However, coconut oil is so good at stripping oil that it can be drying. A 100% coconut oil soap will clean your skin so thoroughly it might squeak. Imagine a soap that attacks grease with enthusiasm. Soap makers usually mix it with olive oil to balance the aggression with softness. Olive oil makes slime. Pure olive oil soap, Castile, doesn't bubble much. Instead, it produces a unique, stringy lather, often described as slime. This sounds unappealing, but it is incredibly gentle. Because olive oil is high in oleic acid, it conditions the skin deeply. Imagine washing with a silky lotion that doesn't foam. It is perfect for babies or sensitive skin. It teaches us that clean doesn't always have to mean bubbly. The cleaning happens silently, without the fanfare of foam. Castor oil stabilizes the foam. If you have ever blown bubbles that pop too fast, you know the disappointment. In soap making, castor oil is the secret weapon. It contains ricinoleic acid. This unique sticky oil acts as a humectant, drawing moisture to the bubbles. It makes the bubble walls stronger and thicker. Imagine adding sugar to egg whites to make meringue. Castor oil stabilizes the lather, turning fleeting bubbles into a thick, shaving cream-like foam that lasts for minutes. It provides the architecture for the luxury. Melt and pour skips the danger. For those afraid of handling lye, there is melt and pour. This is pre-made soap base that has already been saponified. You simply melt it in a microwave, add fragrance and color, and pour it into a mold. Imagine crafting without the chemistry. It allows for incredible creativity, embedding toys in soap, layering colors, making soap that looks like cupcakes. It democratized soap making, turning a dangerous industrial process into a safe kitchen craft. It let us play with cleaning. A soap saver extends life. A bar of soap sitting in a puddle is a dying bar. The water dissolves the bottom layer into a gooey mess called gel. A soap saver, a textured pad or a draining dish, lifts the soap up. It allows air to circulate underneath. Imagine putting the soap on stilts. By letting it dry between uses, a bar can last twice as long. It is a simple tool of economy, saving the soap from drowning in its own element. The largest soap mosaic. In 2018, a team in Vietnam set a world record by arranging 15,000 bars of soap into a giant mosaic depicting a famous opera house. Imagine a floor covered in scented tiles. The artwork smelled of jasmine and rose. It shows that soap, usually a uniform industrial brick, can be a unit of art. Like pixels on a screen, the bars combine to create a larger picture. It turned a disposable object into a monument. Soap film mimics Jupiter. If you look closely at the swirling colors on a giant soap bubble, you are seeing fluid dynamics in action. The turbulence patterns mimic the storms in the atmosphere of Jupiter. The great red spot and the bands of the gas giant follow the same laws of physics as the microscopic swirls on a bubble. Imagine holding a planet in your hand. The scale is different, but the math is the same. The bubble is a model of the atmosphere, a weather system made of detergent and water. The floating egg test. Before pH strips, how did you know your lye was strong enough? You used an egg. Settlers would float a fresh egg in the lye water. If the egg sank, the lye was too weak. If it floated with a patch of shell showing the size of a dime, it was perfect. If it floated too high, it was too strong and would burn the skin. Imagine relying on a chicken egg to prevent chemical burns. It was a rough, biological measurement tool that guided soap makers for centuries. French milled means triple grounded. We return to the luxury of French soap. To make it, the soap is passed through heavy steel rollers not once, but 3 times. This crushes the crystal lattice. It mixes the fragrance and color perfectly evenly. Imagine kneading dough until it is perfectly smooth. The resulting bar is dense, uniform, and polished. It wears down slowly, keeping its shape until the very end sliver. It represents the triumph of manufacturing over the chaotic nature of raw ingredients. Soap is a lubricant. Soap is slippery. Dry bar soap is an excellent lubricant for wood screws. Rub the threads on a bar of soap, and the screw drives into the wood with half the effort. It also unsticks zippers and lubricates drawer runners. Imagine soap as a solid oil. It reduces friction. It is a household mechanic, solving problems of resistance with a simple rub. It helps things glide. Gardeners use soap on aphids. We mentioned drowning insects, but the application is specific. Insecticidal soap is a potassium soap made from fatty acids. It must touch the insect to work. Once dry, it is harmless. It has no residual poison. Imagine a weapon that only works when wet. It allows gardeners to protect their roses without poisoning the bees that visit later. It is a targeted, gentle intervention in the garden ecosystem. Spectral swirling is the color dance. The specific movement of colors on a bubble has a name: spectral swirling. As the water drains down due to gravity, the thickness of the film changes, shifting the colors from red to green to blue. Near the end, chaotic flows appear, swirling like oil on water. Imagine a mood ring made of air. The bubble is constantly telling you how thick it is by the color it wears. It is a visual countdown to the pop. Bubbles merge to save energy. When 2 bubbles touch, they often merge into one. Or they share a flat wall between them. Why? because sharing a wall reduces the total surface area. Nature is lazy. It wants to use the least amount of energy possible to maintain the structure. Imagine the bubbles huddled together for efficiency. A foam is just a community of bubbles sharing walls to survive. They rely on each other to stay upright. Shampoo bars reduce plastic. The modern shampoo bar is a return to the past. It is simply soap formulated with hair-friendly oils like jojoba or argan, and often a lower pH to prevent hair damage. By removing the water, which makes up 80% of liquid shampoo, we remove the need for a plastic bottle. Imagine a solid puck of cleaning power. 1 truck of shampoo bars equals 15 trucks of liquid shampoo bottles. It is a condensed form of hygiene that helps clean the oceans of plastic while it cleans your hair. Soap was a suppository. In the 19th and early 20th centuries, small slivers of soap were commonly used as suppositories to relieve constipation, especially in children. The soap irritated the lining of the bowel, triggering movement. Imagine soap working from the inside out. While not recommended today, it shows that soap was viewed as a universal mover of things. It moved dirt and it moved bowels. It was the household cure-all. Beeswax adds hardness. If you add a little beeswax to your soap recipe, it adds a sweet honey scent. But chemically, it adds hardness and a bit of shine to the bar. However, too much wax makes the soap draggy and reduces lather. Imagine waterproofing the soap. It creates a barrier on the skin that locks in moisture. It connects the work of the bee to the work of the bath. Clean the World recycles soap. What happens to the half-used bar of soap you leave at a hotel? For years, it was thrown away. Now, organizations like Clean the World collect millions of these bars. They melt them down, sterilize the mixture, and remold them into new bars. These are distributed to developing countries to prevent cholera and pneumonia. Imagine the waste of a luxury hotel saving the life of a child halfway across the world. It turns the leftovers of our travel into a global safety net. Soap molecules align at the surface. If you fill a glass with water and add a drop of soap, the soap molecules rush to the surface. They line up like soldiers. Their water-loving heads stay in the water, but their oil-loving tails stick up into the air to escape the wetness. This creates a monolayer film on top of the water. Imagine a carpet of molecules. This film lowers the surface tension, allowing bubbles to form. The soap coats the water, changing its skin, preparing it to foam. Soap is a mediator. We end with the philosophy of soap. Water and oil are enemies. They do not mix. They separate. Soap is the peacemaker. It holds the hand of the water and the hand of the oil, bringing them together in a micelle. Without soap, we could not wash the grease of the day from our bodies. Imagine soap not as a destroyer of dirt, but as a unifier of elements. It allows the world to flow together. It resolves the chemical conflict, leaving peace and purity in its wake. And so, dear listener, our journey through the chemistry of clean comes to a close. We have traveled from the clay pots of ancient Babylon to the triple milled factories of France. We have seen how ashes and fat transform into white bars of purity. We have watched the spectral swirling of a soap bubble, admiring the physics of its perfect sphere. We have learned that soap is a salt, a trap for dirt, and a mediator between oil and water. It is a simple, humble, object that has saved millions of lives and comforted us with the ritual of the bath. From the floating ivory bar to the spicy scent of Aleppo laurel, soap is a sensory anchor in our lives. It washes away the day. It resets us. It leaves us fresh, calm, and ready for rest. As you lie here now, imagine the feeling of a warm, steamy bath. The water is soft and still. The scent of clean soap fills the air. Lavender, milk, or pine. You are floating, weightless, supported by the water. The worries of the day are dissolving like foam. You are clean. You are safe. The water is warm. Let the bubbles pop softly in your mind, one by one, counting you down into sleep. Drift into the warmth. Wash away the noise. Rest now.